I'm recording this, and you will get a copy of this file by tomorrow. I don't know how much good that'll do you, but in other words, I can write, do whatever I need to. Stuff I would normally do on pencil and paper, I do on this whiteboard. Now, I should have gone ahead and had you email me the material that he gave you for review, because it would probably be easier for me to be able to bring it up on my screen than for you to have to verbalize the problem. But whatever's easiest for you.
Okay, I can just verbalize it. It's not bad.
Okay.
So the first one is y equals sine of x to the x. And I'm supposed to use, and the sine x is in parentheses. So.
That actually does make a difference.
Yeah. And it says use logarithmic differentiation to find dy of dx.
Okay. So the first thing we want to do is what?
Take the log of both sides.
Uh-huh. Now what?
Now we move the x to the front.
Now?
One second. And then we can take the natural log of y.
We can differentiate both sides now.
Okay.
Okay? So, to differentiate the left side, what do we get?
We get 1 over y.
Right? Mm-hmm. In other words, we have to implicitly differentiate the left side. So we have to follow it with a dy dx. And then the right side?
Wouldn't it just be the natural log of cosine of x?
Well, we got to use the product rule and the chain rule.
So it'd be the natural log of.
Okay, so the first term we're gonna use, we're gonna let x times the derivative of this. In other words, I'm not sure which way you're going. Since we're going to be adding, you can do either one first.
Okay.
So we'll take x times the derivative of this plus this times the derivative of x.
Okay.
So x times the derivative, what's the derivative of natural log of sine x?
I'm really not sure.
It's 1 over sine x times the derivative of the inside. In other words, we need to apply the chain rule.
Times cosine.
Uh-huh. So that's the first part, plus, and I don't really need to follow it with a dx, because that's always going to be 1.
Okay.
So when I run into x, I don't need to follow it with that. But when I run into any other variable other than x, I have to follow it with the differential. And the right part of this?
Would just be natural log sine x times cosine?
No, because we didn't take the derivative of this. We took the derivative of x.
Oh, I understand.
Okay, okay. So now you can see what the next step's going to be. Remember, we're trying to solve for dy dx.
Okay, so divide by y.
Well, multiply both sides by y. Since I'm running out of room. So there's one answer, if you like. the other answer I could do, if I wanted to, you don't need to, because when you do implicit differentiation, you frequently end up with both x and y in your answer. But if I wanted to, I could substitute sine x to the x for y.
Okay.
In other words, like this. If it made it perhaps easier to simplify, I might do that. But that doesn't look like a piece of cake at all. So.
Well, that's can I read you his answer?
Sure.
So, one is x times sine x to the x minus 1. And then the next
Hold
one
on,
is...
hold on, just 1 second. One is x times sine x to the x minus 1 up there?
No, sine x is in parentheses, and then it's just x.
Minus 1 there.
Yes.
Okay. What's the rest of it?
The next one is cosine of x in parentheses.
Is this plus?
Oh, no, this is a different answer. It's a multiple choice question.
Oh, okay. Hold on.
Sorry.
That's all right. I didn't realize that. Okay. What's the other one?
Cosine of x in parentheses to the x plus sine of x natural log of x.
Okay. What else?
Sine of x in parentheses to the x natural log sine x. Then another was sine of x in parentheses to the x bracket x cotangent x.
I like that answer already. Why? Because this cosine x over sine x is cotangent. None of the other answers have a cotangent in it. But
the last two do.
Oh, okay. But we're also going to multiply sine x times that. In other words, when I go, oh, hold it. Oh, there's a missing x there. So that's, okay. That's not necessarily the answer, but, okay, so I'm sorry. This was x cotangent x?
Cotangent x plus the natural log of sine x.
Well, that's what I've got.
And then end bracket.
Notice how that's the same thing as I got up here?
I do. Okay, so
all I got to do is change that to cotangent x, and that's what this answer is.
Okay, so let me do that real quick.
So it was important that we substituted back in for y in this case, since it was multiple choice. Now that's an interesting non-distribution here. I guess, what would this be just out of curiosity, algebraically? What's that equal to?
Sorry?
What's this equal to over here?
I have no idea.
Same base, different exponents.
So just x?
Subtract the exponents. There's a 1 here. So it'd be sine x to the x minus 1 with the x minus 1 and the exponent, like that.
Gotcha.
Okay. I wasn't sure how we were going to do that when I first looked at it, but I think that's what you would do. Can I erase this?
You can.
Okay, actually I don't need to if we go into a new problem here.
The next problem, I'm pretty sure I got it right.
Okay.
Yeah, I see what I did wrong. Okay, so that one's fine.
That's good. It's taking you so long because that means you must understand most of it pretty good.
Oh, sorry, I'm just trying to give myself room for the next one.
Oh, okay.
Um,
Oh, I thought you were looking for one to do.
oh no, I do not understand this at all. So this one says, the table below shows the velocity of a running dog during a 35-second time interval. Use the right endpoint values to estimate the distance traveled using 7 intervals of length 5.
Okay. How fast can you take a picture of that and email it to me?
What's your email?
I'll write it on the screen. That'll save me from having to fill out the table.
Just sent.
Okay? Can take a while sometimes. Longer than one would think. So they don't want us to use the trapezoidal method. They want us to use rectangles.
I
Right
I
endpoint
have no idea.
rectangles. It sounds like.
Sure.
I mean, from what you read, that's what it sounds like they wanted. This didn't download. Why did this not download? Oh, there it is. Yeah, the computer kind of acted a little funny. Didn't show the file downloaded there like it normally does.
Can you see it all right?
Yeah.
Okay. Sorry, sometimes it just doesn't work well.
Okay. This basically, the concept here is integral as net change. In other words, what we're looking at is a derivative. The velocity is a derivative. So if we want the total distance traveled, we want the area under the curve. And this is not a continuous function, so we don't have a function that we can integrate and evaluate between 2 points. But its next best thing is it has 7 points on it, so we can certainly use rectangles to come up with the area under this curve. In other words, our curve really is made not up of a straight line, but points. There's a point here. Let's see, 0 is 18, 5 seconds is 22, 10 seconds is 28, so forth. In other words, if I were to graph that table. You with me?
Mm-hmm.
Okay, there's 5, there's 10, and so forth. And they say use right endpoint values to estimate it. Well, they're talking about right endpoint rectangles using 7 of them.
Okay.
So over here, let's see. Let's make sure we got the right number here. That's 20. That's 35 right there. So how many intervals do I have here? 1, 2, 3, 4, 5, 6, 7 if I use right endpoints. And 35 was all the way up to 30. So the rectangle I'm going to use here is that rectangle.
Okay.
And the rectangle here is going to be that rectangle. Okay? And we're going to add up the areas. The width of each of these rectangles is going to be 5. The height of this first one is 22.
I understand. Okay.
Now, I'm a little hesitant here. I guess if they would have said use left endpoint rectangles, then the first rectangle would have been that one. And the second one would have been that one.
Yeah.
But when they said right endpoint, the first rectangle, the only right point I have is the second point here. And that gives me 7 rectangles also. So I'm fairly confident that that's it. What's this answer is one you wrote?
Yeah, that's not right. We weren't sure what we were doing.
Okay. Well, yeah, it's just 5 times the height for each rectangle. In other words, you're going to have 5 parentheses these 7 numbers right there.
Yeah, I just did that and I got, 1 second, 930.
Okay. Yeah. Okay. Let's see. Are we good to go to 5 here?
I believe so.
Or do you know how to do 5? Do you not need to go to 5?
Did I get 5 right? No.
Almost.
Okay. Well, that's encouraging.
Take away this 4 and you got it just fine. In other words, what we're dealing with here is the fundamental theorem of, here, hold on a second. Hold on.
Do you want me to email all the pictures to you?
Email, well, it depends on how hard it is to verbalize. That table was going to be hard to verbalize. This problem, on the other hand, wouldn't be that hard to verbalize. But let's talk about this as long as I'm looking at it here.
This is actually the last one I need help with.
Okay. All right. If I said this.
Well, there's 2 more that I'll send you, but.
Okay. And that's equal to y. And I said take the derivative of that. In other words, what's dy dx? When you take the derivative of an integral, what do you get? If it's a straightforward integral, like this one is, then you get the function.
Okay.
Okay? In other words, the t is a dummy variable. Doesn't matter. As long as it goes from a constant on the lower end of integration to a single linear variable, then you just replace that variable wherever you find the dummy variable they have. When you go to x to the fourth, I think you might have gotten this right now that I think about it. I'm going to have to look this up because I'm not 100% sure, but I know exactly where to look. It's in your book. Let's see. This is going to be after the fundamental law of calculus, theorem of calculus. Yeah. I'm looking at it here. You did do it exactly right.
Oh, okay.
In other words, I wasn't sure. I knew we had to substitute x for our variable, or x to the fourth, one or the other, and then you have to multiply it by the derivative of that. In other words, you have to apply the chain rule.
Okay.
So it's going to be times d of x to the fourth, and this is x to the fourth. So you did get it right.
Okay. And then I sent you...
Oh, yeah, okay. You multiplied the 2 to get the 8x. Okay.
Okay. I just didn't know how many points it was worth, so...
Uh-huh.
And then I emailed you a picture. So.
What the heck is going on with my email program here? This is weird. It didn't show your other emails. Or is this the same one?
No, it's a different one.
It's a different one. Okay, let me close that first one out and make room for this one.
I'm not sure what I did on this one. I got it wrong, right?
Which problem?
Both.
3?
Well, that one I just missed a negative sign for A.
Okay. Let me just look at the
And this
problem.
One, that was related rates, if I'm not mistaken, and I actually got that one right, and I was struggling with related rates. So.
Okay. Yeah. When you plugged in for dz dt, what'd you put in? You put in 2.
Yeah.
I think it's minus 2.
Okay.
In other words, because he's pulling on the rope, dz dt is getting shorter. It's not.
Oh, okay.
It's not getting bigger. In fact, let me bring up one that I had confusion on, and after thinking about it, I realized something, and that is the ladder against the wall, where here's my ladder, and a kid is pulling on the bottom of that ladder with his wagon, and I kept thinking that dx dt needed to be negative because he's pulling to the left. And I couldn't get the problem to come out right. My sign was off. And it took me a long while to realize that it's not which direction it's going. It's whether it's increasing or decreasing. And when the kid is pulling on the ladder, dx dt is getting bigger. So it's positive.
And dy dt is getting shorter?
Yes. And
okay.
dy dt would be a negative number. Well, in this case, because he's pulling on the hypotenuse, that has to be negative. Now, what did they want? They want how fast is the boat approaching the dock. So they want dx dt. and you came up with
The
2.5.
right answer is wrong.
No, you got it right. There's a note here that it's negative the way it should be negative, and it will be if you put in a -2 there.
Okay.
This whole thing will come out negative, and since dx dt is shrinking, again, this is very similar to my ladder against a wall problem. It doesn't matter whether he's going to the right or to the left. The fact is that dx dt is getting smaller, so it needs to be negative.
Okay.
At what rate is angle changing at that moment? So the angle is equal to, or the sine of the angle is equal to x over c, and we want d theta dt. So we need to bring in inverse functions here. In other words, here, sometimes a little tricky to get this thing situated just right. You don't have a big enough monitor. I need a monitor like is on that computer in your dad's house.
Yeah.
Sine alpha equals x over z. So what does alpha equal?
The cosine of?
The inverse sine
Oh, okay.
of x over z. And so d alpha dt is what they want us to solve for. This is her note over here.
Yeah, that's his.
So she made it 2. Oh, that's after you're finished with it. Okay. This is your work here? And
Yes.
and these are her notes in blue? So she's indicating you did it correctly.
Oh, is she?
Well, I don't know. In other words, I'm thinking that the only way I can think of to do this is to solve for alpha and then take the derivative relative to t implicitly. And I still think that that's what we're supposed to do. So dA dt is equal to what?
The inverse sine of, oh, the inverse cosine, right?
No. What is the derivative of inverse sine?
Ew, I hate that.
It's one of the harder ones to memorize. I'm lucky I got my second calculus book here because I open that front page and it gives me all of them.
Isn't it u primed over the square root of 1 minus u squared?
Okay, the derivative of inverse sine of u is equal to u prime over the square root of 1 minus u squared. Is that what you said?
Yeah.
Okay. Now, not that that's going to be that easy to figure out here, but let's see. So we're taking the derivative of that, and x over z equals u.
Okay.
Okay? So u prime, oh man, really?
But what about the alpha? Oh, okay. I see it. Never mind.
Okay. Yeah, once we figure out how to differentiate this thing, then Okay, let's see. Let me see if I can give it a shot here. It's 1 over the square root of 1 minus x over z quantity squared times the derivative of the inside and the derivative of the inside we're going to have to use the quotient rule on. In other words, what is u prime? That's why this u prime is here. That's the derivative of the inside. Okay, so let's see. What do we got? We got the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That looks a lot like what you got there. Yeah, that's why she not quite sure how you got this. Without first, well, you must have realized that, you must have realized you were doing inverse sine, even though you didn't put that step there.
Well, all I did was took the derivative of both sides, and I realized I'd use quotient rule.
Yeah, the only thing it looks like you left out was this part here, which would be this part here, I guess. In other words, I don't see this anywhere on yours. So now, this right here is d alpha. That's going to tell us the rate at which alpha is changing with respect to time. And we're going to substitute everything we know about x, z, dx dt, and dz dt. Because we figured out both of those in the previous problem. My problem is, I don't have it. Let me go. Okay. So, dA dt is equal to 1 over the square root of 1 minus, what are x and t in this problem? When you're 10 feet, x and z rather. Z is 10. Yeah, and x is 8. So 4/5 squared times 10. dx dt ended up being negative 2.5, right?
Yeah.
Minus 8, and dz dt, what was the rate?
I don't remember.
Minus 2 feet per second.
Yeah.
So minus 2. And in this problem, those minus signs might not cancel out. It didn't make a whole lot of difference when you did it that you got the sign wrong, because, I mean, it kind of did. The answer was minus 2.5, but in an absolute sense, you got it right. Over z squared, which is 100. So I think it's just a question of solving that or doing the arithmetic.
Okay, let me do that.
Yeah.
So,
Yeah, it's probably better if we spend our time on the setups on these.
okay. Well, that
Okay.
is all I
Is that it? Is there a C part to that?
There is
No?
not.
Okay. Any other problems you want to go over?
That was all I had trouble with really on the test.
Okay. Cool.
Thank you very
I
much.
remember, yeah, I remember this problem here. We did a problem like that once. And
Yeah, we did.
I seem to remember that the first time through I forgot to do solve for theta. But I wonder why she put the parentheses around. What is that, cosine x?
It's cosine alpha.
Cosine alpha? Okay, I see what happened. You took the derivative. Okay, so you took the derivatives of both sides, which you could also do. Yeah, this isn't actually a wrong way to do it. Curious if this gives you the same answer.
I'm almost done plugging it in.
Because you did end up taking the inverse cosine at this point. Well, you got cosine, not really.
No, I got negative 0.15 rather than 0.9. I mean 0.45.
0.45 is the right answer?
No, I got 0.15.
When you did it by doing the inverse
Yeah,
immediately, you got 0.15?
yeah.
We don't know what the correct answer is?
No, we do not.
Well, I guess we're going to have to just leave it at that. There is perhaps, this might give you the same, it looks like this gave you 0.45 instead of 0.15, but who knows, there might be a math error in there or something. I think you would have to solve for dA dt. You're going to have to not take the inverse here, but divide everything by the cosine of theta, or the cosine of that angle. And we'd have to know what the cosine of that angle was.
Okay.
So you could kind of do that. It's a 3, 4, 5 triangle. You could put a number on the cosine of that angle at that point in time. I'll bet you this gives you the same answer. If you go through the math doing it this way, that might work. In other words, you don't necessarily have to do a first step of solving for theta and then taking the derivative of the inverse function, although I'm pretty sure that's probably the best way to do it. But
Okay.
this way, there's nothing that keeps you from taking the derivative of both sides, which is all you did. Now, this should work, actually. Might actually be easier than dealing with that inverse tan function. I don't know whether it's worth your time to go through and find that out or not. But the only thing I see wrong here that you did was you took the inverse instead of dividing both sides by the cosine of alpha.
Gotcha.
Okay?
Gotcha.
All
Thank you
right.
very much.
You're welcome. You're a hard-working girl. Sounds like. Sounds like you're very busy. But
Yeah.
I hope I've been helpful, and good luck on your test.
Very helpful. Thank you very much.
All right, Emily. You still need Sunday at 4:30?
Yes, please.
Okay. I'll see you then.
Thanks. See you then.
Bye-bye.